Okay, so in this part, I want to just go over another example. This is example 1 from the book um, about what happens to theorem 12.1, which we just proved, when you don't assume that the sequence Sn converges to a positive number, okay? The requirement of the limit S being positive is actually very important. And the theorem just kind of completely breaks down if you don't assume that the limit is positive. The cases where the limit is negative kind of obviously don't work, because if you multiply, okay, let me write this down. In theorem 12.1, if S is less than 0, then we should expect something more like we would expect something like lim sup Sn Tn equals, so S, remember, is the limit of Sn, right? So we're assuming that Sn converges to a finite negative number in this picture. So we would expect something more like S times the lim inf of Tn, right? Because basically, multiplying by a negative constant should just reverse the lim inf and lim sup of Tn. So actually, the greatest values of the product sequence we would expect to be coming from the lowest values of Tn. Okay, so that's kind of the reason why the original theorem sort of obviously breaks down if the limit is less than 0, but it also breaks down if the limit equals 0. So let's talk about that, because it's a bit more interesting and more nuanced. So this is what their example deals with. If the limit of Sn equals 0, then oops. Let me just define. So consider, their example is this. So they say Sn is negative 1 over n, and Tn is negative n squared, right? So then Sn Tn is just n, okay? So the left-hand side is infinity, and the right-hand side is the indeterminate form, which I'll put quotes around, is 0 times, right? So 0 is the limit of Sn, and then the lim sup of Tn is negative infinity, right? So this equation, setting these equal to each other would be ridiculous in many ways, right? The first being that, for one thing, this is just not even a sensible expression in the first place. But even if we were to try to make sense of this expression, there's no world in which it would be reasonable to evaluate this as positive infinity, right? That's what they kind of get at in the book. So this is one example of why letting Sn approach 0 breaks theorem 12.1. For now, I want to give you guys a lecture question, which involves breaking this in a little bit more of a subtle way. So give examples, or give an example of Sn and Tn where the lim the limit of Sn is 0. The lim sup of Tn is a finite number, and the lim sup of Sn Tn is strictly greater than 0, so positive. So this is basically, here it was like, well, we took a sequence where the lim sup of Tn was negative infinity, and then we ended up with this crazy nonsense. But you can actually break this in other ways, where you can actually make this lim sup be like a finite, and let's say we want it to be finite. You can make this be a finite positive number. You can make this be a finite number and this be 0 and end up with an equation that still doesn't work, right? Because if this is positive, then obviously it's not equal to 0 times this number, right? So pause the video, think about it, and I'll explain when you unpause. And do remember, so this is lecture 7, question 1. So remember to include this on your homework. Okay, so the example I had in mind for this was the following. So let's take Sn equals -1 over n again, right? And then Tn, we could do something like this. We can make it be 0 when n is odd, let's say, and then -n when n is even. I believe this should work because now, so SNTN equals 0 when n is odd and 1 when n is even, right? So clearly the limit of Sn is 0. The lim sup of Tn is also 0, right? Because it keeps alternating between -n, which just goes to negative infinity, and 0, which just stays at 0, right? So the lim sup of Tn is 0, and then the lim sup of SNTN is 1. So yeah, that should do it, I think. And that's all for this video. In the next one, we will move on to talking about some ways of using lim inf and lim sup to estimate exponential behavior in a sequence.